Okay, video 2.3. All I'm going to do now is an example showing you how we can do some statistical tests, how we can maximize the likelihood function. And all I'm going to do is go back to the case where we talked about in session 1, where I said that there was theta equals the probability that the largest party is selected formateur in a parliament. We had 3 cases, and we had our x xi. We only had 3 cases, and that equaled 1, 0, 1, where the x only had our dependent variable. There were no independent variables, and so we had the first country, largest party was selected formateur. Second country, it was not. Third country, it was. Okay. Now, once we did this, remember the likelihood function in this case would just equal theta times 1 minus theta times theta equals theta squared 1 minus theta. Okay, and then we took the maximum of the likelihood function. So, and then I discussed this, why if theta hat maximizes the likelihood, theta hat will also maximize the log of the likelihood. So we could do it either way. I could take the log of it, take the derivative to find theta hat, or I could just do it directly, take the derivative of this with respect to theta, set it to 0. Either way works. It's a little more useful to take the log because I'm about to take the second derivative of the log. And remember I told you, okay, when you want to do statistical hypotheses, you need the variance of theta hat, and it's all related to the second derivative of the log of the likelihood. So let's take log L of theta, and that is just going to equal to 2 times log of theta plus log 1 minus theta. Okay, hopefully everyone remembers these log rules from freshman calculus. Okay, so now let's take d theta log L of theta. That just equals 2 over theta plus 1 over 1 minus theta times -1, because we have a negative theta there. We're going to set that equal to 0. And so that means that 2 over theta equals 1 over 1 minus theta, which means 2. So multiply both sides by 1 minus theta. So we get 2 times 1 minus theta, which is 2 minus 2 theta. Multiply both sides by theta. We get theta equals theta. And so that says when we've set the derivative equal to 0, theta is going to equal 2 over 2/3, by the way. So 2 is going to equal 3 times theta. That's where I get that. I skipped one little step of arithmetic. Okay, so the theta that makes the derivative equal to 0 is theta. Now we're going to call that theta hat. That's defined as our maximum likelihood estimate. Okay, for this case, our maximum likelihood estimate of theta is 2/3. Okay, now let's do some statistical hypotheses. Let's now get an estimate of the variance of that theta hat. Okay, so that's our estimate is 2/3. What's our estimate of the variance of it? And the way we do that is we just take the second derivative. Take d squared d theta squared of log L of theta, and that is just going to be the derivative of all of this stuff. Okay, so that is going to equal, let's see, 2 over theta squared times -1. Okay, so it's 2 times theta to the -1. I can't remember the rules from what we called the rules from freshman calculus, but we have to multiply that by -1 because we have an exponent of -1 on that theta. Then we have, it's minus, okay, now we have 1 over 1 minus theta squared. Okay, because we've subtracted 1 from that exponent. We have the exponent of -1, so it's -1. But then we have a negative theta, so we're going to have to multiply that by -1 again. And so that is going to equal -2 over theta squared minus 1 over 1 minus theta squared. Okay, did I get that right? 2 over... Right, okay. And then, hope you will trust me if you get a calculator, and so Kramer has shown when we substitute our maximum likelihood estimate of theta for our value of theta, so we substitute 2/3 in for theta. When we do that, that operation is going to be right in the limit. It's going to be correct in the limit. Let's assume we have enough data so that we're close to that, although we have 3 observations. Maybe that's not such a good assumption. But let's do it anyway. So what that means is that the second derivative is going to equal... Second derivative is going to be -2 over 2/3 squared, so for 4/9, minus 1 over 1/3 squared, 1/9, and so that is going to equal -2 over 9/4 minus 9, which equals -13.5. Okay. Okay. Now, remember what we want is first, if we look, fortunately, I already erased the board. Remember, so what we took is the second derivative of the log of the likelihood. We take the negative of that. Okay. So let's take the negative of that. We get positive 13.5. And then, remember, we took the inverse of that value. And so that equals about 0.0741. Okay, so variance of theta hat is approximately equal, so in the, well, asymptotically it would exactly equal, but so we know that an approximation or a good estimate of the variance of theta hat's got to be that 0.0741. Standard error of theta hat is the square root of that, and that equals 0.2722. Okay, so if we were going to do, say, a t-test to say, can we reject theta hat, our estimate, can we reject the null of it being 0, 0.667 divided by 0.272, that's going to be over 2. That's going to be over 1.96, so we can reject. That would be a case we can reject. Even though we only have 3 observations, we could actually reject a null in this case. Okay, so we've done an example where we've computed the maximum likelihood estimator. We use that value that Kramer and others have proven, and we know that that's in the limit, got to look like a normal distribution, and we can actually run statistical tests to test a null hypothesis. Okay, so that is our first example. Okay, so that is, gosh, I'm already forgetting. I think I'm right. This was 2.3. I'm almost certain that's right. 2.3, maybe it's 2.4. Okay, see you in the next video.